And let's see, what were the questions? 32, 33? Okay. So, let's see, what does 32 say? Write a procedure double tree that takes a binary tree, as we represented in 1.17, and that we have functions for from 1.31, right? Where are we at? And produces another binary tree like the original, but with all the integers in the leaves doubled. Okay, fair enough. So let's go back in here. So here's all of our constructor stuff for our binary trees, right? And we have the ability to check whether something is a leaf. And if something is a leaf, then what do? That means it's a number. So in this particular case, we're going to traverse a binary tree, build a new binary tree that is identical to the original binary tree with all leaves replaced with a value that's twice what they used to be. Right? And don't we have a constructor for a leaf? That we just pass a time, whatever it used to be times 2? Okay. So it's called a double tree. Define double tree to be a lambda that takes a bin tree as a parameter. And then we're going to walk through that binary tree. So how do we know when we're done? And how do we build binary trees? What is a binary tree? What does it look like? How is it represented? Go ahead. Okay, it's a tree of trees. And are we representing them as lists? All right, so when we, now, what's the simplest binary tree? So could we just have, is the value 5, is that technically a binary tree? All right, so potentially we can have a tree that is nothing more than just a number. So we can't necessarily just end on the empty list, correct? Because I might be dealing with a tree that's just a number. Okay, so if a tree, so we can go ahead and just start asking some questions. So we can say, if leaf, you can do it. There we go. Leaf bin tree. If that's a true statement, what do I want to do? What should I return if I'm looking at a leaf? Just be a number, right? That's true, but what am I supposed to do with numbers? I'm supposed to double them, right? So now, you could just return the thing that's just a number, but really we should use our constructor for leaf to define a new leaf that is the old leaf times 2. That would be the most accurate way of representing it. Does that make sense? So what we would return here, if we're looking at a leaf, then we're going to build a brand new leaf that is going to be 2 times the current tree. Make sense? Double the leaf. Even though we know that leaf of this is just going to boil down to a number. So you could have just returned times 2 bin tree, and that would have been okay. But this is using our constructors from the previous thing. So we're constructing a new leaf. Else, if it's not a leaf, I must be dealing with a what? I must be dealing with a tree that has a symbol followed by a left and a right sun. Okay? So if that's the case, what do I do? Well, if I'm looking at that version of a tree where I have a symbol and a left sun and a right sun, where the left sun is a binary tree and the right sun is a binary tree. Do I need to do anything special with, do I do any doubling with that? Do I have to multiply anything by 2? At that top level, right? Go ahead.
Wouldn't you multiply the value you have?
I don't have a value, I have a symbol.
Huh.
Yeah, only that's what this thing's supposed to do, right? Only the numbers. Ready procedure, double tree takes the binary tree as represented in definition 1.17 and produces another binary tree like the original with all the integers and the leaves doubled. So only leaves are we doubling. Otherwise, the definition of our binary tree for a node is a symbol followed by a binary tree followed by another binary tree. Is that correct? Sound right? Okay. So if we aren't looking at a leaf, we must be looking at a binary tree. Is there such thing as an empty binary tree? Open parenthesis, close parenthesis. Is that covered by our definition for binary tree in 1.17? I don't believe it was. I'm really trying to not have to go look at 1.17, but I'm not getting a whole lot of.
Well, I think you're right.
Well, I'm almost positive I'm right. There's a first time for everything, I suppose.
It's
But
like, I don't know.
it's a who?
Was it, what page was it? Was like
1.1.7.
Yeah.
Yeah, so a binary tree is either an int or it's a list with 3 things in it. There isn't a binary tree that is the empty list. All right, so if I'm not looking at a number, I must be looking at a list of 3, a 3 list. Okay. So what was the 1.3? There we go, we're back. Okay, so with that in mind, the else here is I'm looking at a 3 lists. So what am I going to do? I'm going to build. We have a constructor for a binary tree, right? This is called an interior node. So I'm going to build an interior node, passing it my symbol, passing it whatever double on LSON returns, and then passing it whatever double on RSON returns, right? Because LSON and RSON are both binary trees. All right. And do we have a thing to get the contents of this guy, right? Contents of gives us the symbol. All right. So we're going to build an interior node. Is that how is it? Underscore or dash? Dash. I'm going to build an interior node with contents of bin tree. So that'll get me the symbol. Followed by, what is it? RSON and LSON. Which one comes first in the interior node? LSON, okay. So followed by double tree of LSON bin tree and double tree of RSON of bin tree. Think that'll do it? Make sense? Now, how many of you did it this way versus writing in cars and cooters and stuff like that? Who did it this way or something very similar to this? So who wrote a lot of cars and cooters? Who didn't do it at all? So we got a third of a class that said they did it this way. Then we have no hands for the other 2 questions. Okay, so if you didn't use cars and cooters and you didn't do it this way and you did the homework, how did you do it? Am I to assume with cars and cooters? You just didn't answer? Why is this more correct? I mean, it's the same, right? I mean, isn't what we're doing here an abstraction of the cars and cooters? When we're saying LSON of bin tree, under the hood there, aren't we doing cars and cooters of stuff to extract the left binary tree? So why did we say LSON there as opposed to rewriting the code and saying cars and critters there. Okay, well, first of all, this reads better, right? Because what are we saying we want? We want the left son of our binary tree. How do we get the left son? We call lson. That gets us the left son. So it's cleaner anyways. It also forces us to use, it gives us a rationale for those constructors and functions that we wrote last time. Why write them? And it's not just busy work, right? It allows us to represent data in an abstract way that's readable. Because as we've already seen, if things start getting complicated, if we replaced leaf and the leaf question mark and the leaf here and the interior node here and the contents of or the lson or the rson, if we replaced all of those in here with their actual implementations, this would be a pretty scary looking function, wouldn't it? With parentheses out the wazoo. All right, and I mean, I know we're all loving the parentheses, but at least some of you have run into a situation where it's been annoying at this point, right? Or you've had a weird error because of a parenthesis in the wrong place or something like that. So the cleaner, the simpler we can keep it, the better we are. So the more you can abstract your data, you can simplify your data, this kind of is like the evolution of our helper functions that we've been talking about, the better. All right, so any questions about this one? Okay, so now, let me kick this down a line. And what was the other question? Was the other one easy? The other one sucked? All right, write a procedure called mark leaves with red depth that takes a binary tree and produces a binary tree of the same shape as the original, except in the new tree, each leaf contains the integer of nodes between it and the root. That contains the symbol red. Let's see. Except in each leaf contains the integer of nodes between it and the root that contains the symbol red. For example, if we have an interior node, it contains the integer of nodes. Okay, so the number of nodes between the node we currently have and the root that contains the symbol red. So in this case, we are one depth down and we have one red. We are two depths down. All right, so this is returning so a red we leave alone as a red. A bar we leave as a bar, but we replace the two leaf nodes with the number of reds that have gone up to this point. So we have a 1 and a 1. Then we jump down to the next one. So now we're at another red, and we're also at 2 nodes. Then we have a leaf. So this first leaf is, where are we at here? So here's our red from this guy. There's our red there. Then we hit our first leaf, and we have a 2 there because that's the number of reds we bumped into so far. And then we have our next interior node, which is QUX. And then we have a leaf node and a leaf node, also 2, because that's the number of reds we bumped into. Does that make sense? So we're having to count the number of reds we see along the line. Whenever we bump into an interior node, what are we creating? We're creating a list containing the symbol of that interior node, along with our call to the mark leaves with red depth thing again. But we're going to have to pass in a constant count. So we're probably going to need, by what we've done up to this point, we're going to need a helper that takes an account, and we'll start off at count 0. Make sense? All right. So we're going to call this helper red depth helper because that's a lot of crap to type. All right. So we're going to define red. Am I doing underscores or dashes? There we go. red depth helper. Oh, I had an interesting conversation with Dr. Pavel at lunch today regarding our Luke 1 incident. Yeah, he had never seen that before, he said. He said, yes, that does sound funny. So it was fairly entertaining conversation with him, as you might expect. All right, red depth helper. So this is going to still take our, let's see, what are we going to take? Our binary tree, but also a count. Right? We're going to need our binary tree, the dude to traverse, but we also want to keep track of how many reds have we seen. All right. This guy is going to be a lambda that takes in our bin tree and takes in, call it num reds. Okay. Something like that. Now, let me just close this here for a second. I'm going to go ahead and, what's this guy supposed to be called? Mark leaves with red depth. This guy would be a lambda that takes in a bin tree, and all he's going to do is call red depth helper bin tree 0. Make sense? He's going to get that ball rolling with, I've never seen a red up to this point. Okay? So now we'll go up and finish writing this guy. All right, so here's the body of this lambda. Now, let's go back here to this. When we bump into an interior node, what do we do with it? We cons the symbol of it onto a list. But we must also consider the contents of that, right? If it is equal to a red, then we want to increment our count. Okay? So, if we're dealing with an interior node, as opposed to a leaf node, what do we do with leaf nodes? Leaf nodes, we cons on the actually, are we going to want to do a cons, or are we going to want to make a list? I think we want to make a list here because we're never going to actually get to, yeah, we're never going to get to the point where we're going to have an empty list. So I think what we want to do here is we're going to ask if we're looking at an interior node, and we have a predicate for that, right? This guy right here, interior node. So we'll say if interior node bin tree, if that's the kind of guy we're looking at, then we have two possibilities. This is a interior node who has a symbol, who has a, what's it called? Contents of red. So we're going to say EQ question mark red contents, and I'm going to have to throw an if in front of this. So if the contents of the binary tree is a red, if that's a true statement, what are we going to do? We're going to create a list containing, we know it's red, so we could just say red there. That'll actually be faster since we don't need to resolve it. Does that make sense? Or you could also say contents of again and extract it if you want. But we wouldn't be in this guy here unless the contents of our binary tree was red. So we're going to go ahead and create a list out of red along with red depth helper, passing it our LSUN of our bin tree along with plus 1 numReds. That's our first call to red depth helper. Second call to red depth helper, and actually I'm gonna, we'll keep it all on the same line, I guess. Well, let me kick it down. I think it'll read better if I do it like this. My third parameter to this list, so first list is going to be the red. Next parameter is going to be, or next element of my list will be whatever red depth helper returns for the left son of my binary tree. And since I just saw a red, I'm going to add 1 to my number of reds. And then red depth helper for my arson. Arson. Get it? I hate you all. That's recorded, so you can take that to the judge. All right, so, and there's the end of my list. So we're creating a list here that will have red depth helper for the first stuff, red depth helper for the second stuff, left son, right son, with one additional thing. Now, if I'm in this else here, what does that mean? If I'm sitting in this else, what do I know to be true? Go ahead. Okay, I know it's an interior node, but I also know that the symbol, the contents of it, is not red. Therefore, I'm going to go ahead and create a list, passing it contents of I feel like I'm typing poorly today. I need like a designated hitter. See, it's left over from the tremors. I started getting tremors in the right hand too. I'm gonna be flopping all over the place before too long. What are we gonna do? What was I talking about? Oh, contents of my binary tree, because now we don't know what it is. We just know it's not red, right? It's something else. So we're gonna create a list out of whatever it was, then pass it my red depth helper for elson bin tree and whatever numreds currently is. Oop, not done yet. And I'm going to kick this down the line just so it's similar to what we had above. And then the third parameter will be red depth helper arson bin tree numreds. Because we did not see another red, therefore we're going to create our list here, and we're going to call our red depth helper again on the left and the right, but we're going to pass it the current number of reds we've seen. We haven't seen a different number of reds. Make sense? So if it's equal to red, do that stuff, else do this stuff. All right, so that's if we are in an interior node. So if I'm at this else, what's true? So this first if says, if I'm looking at an interior node, check to see if the contents were red. If it was, do this stuff. Otherwise, do this stuff. If I'm here, that means I'm not looking at an interior node. I must be looking at a what? A leaf. And what am I supposed to do for leaves? Return the red number. Oh, is this my application? There we go. So if I'm looking at leaves, then I'm just going to boil down to num reds. That. I'm very disappointed in the number of single quotes I'm going to have to fix here. 1. They didn't even write that right, did they? Yeah. The book can't even get parentheses right? How many parentheses are we missing here? That's an interior node. All right, so that's what the book wrote. So this is the interior node that is the right-hand side of this interior node. So that's the finishing thing for that, right? And here's an interior node whose symbol is red, whose left sun is that, and whose right sun is that. Therefore, we have that, and then that. I look accurate now? That's kind of crappy of the book, isn't it? Good for the reader.
Probably start over with your book.
You want the old version? The old, which I actually prefer. I like the original, but there's way more errors in that one. You think this stuff would be, you know, what's the thing? You think this stuff is hard now with some errors. Think about how much harder it would be if it was even more moving targets. It's like you're juggling. What book would you want to switch to? This is fun, isn't it?
Yeah, I like how they give like the sample output for most problems.
See, I like how the book is almost impossible to read. That's one of my favorite parts of it. You like read it and like, what? You know, like it doesn't make a difference whether you're watching Netflix while reading the book or just reading the book. Your comprehension is identical, right?
That's why I always watch Netflix.
Yeah, it makes sense. All right, so I assume this is going to work perfectly. Mark leaves with red depth is used before it, hold on. Where did I use it? Oh, I used it. I get it. Stop. See, I was testing you. Can't call functions before they're in their scope. Red, bar 1, red 2, list 2. That looks right, doesn't it? Yeah. All right, questions about that one? We didn't test the first one, but I'm pretty sure it works. It works? You tested it? Yeah. All right, good. See? Still batting 1,000, waiting for that first syntax error. Okay. So let's get these in Slack. Now, actually, let's talk about this. Well, let me put it in Slack first, just so I don't forget. And then let's, so that's actually the new code that leverages the stuff from before. This doesn't look like Slack. This is Slack. All right, nailed it. Okay, so let's talk about the complexity of the second one, because I think most of you, from what I was hearing from people grumbling about the assignment, the second one was harder. Is that right? What do you think made it difficult? What were some of your challenges on that one? Go ahead.
Struggle a lot and just understanding the input and output the way they wrote it,
Mm-hmm.
and just understanding what they wanted, getting like a mental picture of what the tree looks like.
Okay.
I could not figure that out.
So kind of going from here's your input, here's your output. How did they get that?
Yeah, how did they
So
get there?
before you could write the code from doing it, so this goes back to 150, right, with Dr. Locklear. You know, before you can solve a problem, you have to understand the problem. Okay, so one of the challenges with this is you start getting this almost like cryptic ways of explaining things, right? You have this challenge of initially sitting there, forgetting about scheme and just saying, what is it that they're asking me to do? And make sure that if you had a piece of paper sitting in front of you that had a binary tree written, that you could come over here and write the desired output of it which then proves you know what you're supposed to do. Before you even start trying to do it, because I promise you, if you don't know what you're supposed to do, you're guaranteed to have code that won't work. Okay? I always find it interesting how many students start writing code when they don't know what they're supposed to do. That's kind of like going on a road trip without having a destination. Now, in real life, sometimes you just kind of accept that, right? That's part of the adventure. You know, kind of do a Sheldon, you know, every single time you get to an intersection, you just roll the dice and decide which way you turn. You know, that would become pretty annoying in like cities, but maybe in like the country or something like that, that would be an interesting enough game. Especially if we go back years before we had GPS, where you truly become lost. And now you have to start navigating by like the sun and stuff. Walking up to like abandoned farms. You're spending the night in there, and all of a sudden you hear a shotgun because he wasn't as abandoned as you thought. So it's really, really, really important that you can come to terms with what the problem you're solving is. Now, how many of you struggled with understanding what this question was asking? I would assume several, because it's cryptic, right? Now, how many of you, up until we just solved it, still didn't know what it was asking? 5.5 people? Like, you turned something in, but you weren't really sure kind of even what the question was asking you to do. Like, look, I made some lists and I hope he doesn't notice. It's like that kind of thing, right? How many of you asked for an explanation of how it worked? Yeah. This isn't bad participation. This is the accurate number. So the reason I like to kind of do this the way I do it in here is, I mean, obviously I've solved this question before, but it's been 2 years since the last time I taught this class with this book. So you're kind of seeing me stumble into the question the same way as you're stumbling into the question. I promise you, my mind's not remembering stuff from 2 years ago. So you see that problem-solving approach. I had to read it 2 or 3 times before I kind of figured out what they were trying to get me to do, right? So that's the process you need to go through when you're solving these problems. Spend some time initially trying to understand what they're asking to do. And if you can't, don't just start throwing lists and parentheses. Go on Slack and ask. Can somebody explain what 1.33 is even asking me to do? Your solution's not going to help me because I don't understand the question. Does that make sense? So take advantage of your peers or me and ask those questions, because I promise you, if you don't know what the question is asking you to do, you will not be able to solve it. Right? That goes beyond just scheme stuff. Now, another challenge, obviously, is they gave you some, incomplete test input. But that wasn't that bad. You walk through it a little bit. If you couldn't fix the parentheses in here, that means one of 2 things. You're either really, really struggling in here, or you've developed a phobia of parentheses, which either one of those are possible. Okay? I have had students come out of here who truly had phobias of parentheses. In fact, my new desktop wallpaper on the MSI laptop I'll have tomorrow talks about lambda calculus and a zillion parentheses and something like that. It's kind of a joke wallpaper. Which is kind of interesting. Okay. So make sure you understand what's asking, because that's really the challenge in this question. And, to be honest, had they not given you an input example and an output example, this may have been difficult to kind of figure out what they were asking you to do, because it's a little bit awkwardly written. I wouldn't say it's written perfectly. It's at that point it would be, up to the reader. But does everybody understand what they're asking you to do now? Now, and another thing, this is another interesting question, another interesting problem with this. Everybody in here should have had CSC470, right? Now, in CSC470, I typically cover AVL trees, correct? And so you don't get to use this excuse then. But there is a competitor with AVL trees called red-black trees. So one thing that could happen is if you've been introduced to red-black trees before, which is another self-balancing tree. It's a competitor with AVL. If you've been introduced to that, you might instantaneously read this question as having something to do with red-black trees. You know what I'm saying? And now all of a sudden you're like looking for balancing stuff like that, and that makes it way harder. Okay, so out of curiosity, did anybody in here think about it that way? Thought about red-black trees? Where had you read about them before?
I remember hearing one in the lecture.
Oh, so I mentioned it.
Yeah, I was like, oh.
Gotcha. Yeah, so that would have made it more. That would have made it scarier. I wish I was there actually. For that initial reaction from you when you were thinking red-black trees, like okay.
Oh, shoot.
Yeah. Oh, you probably use more colorful language than that. I mean, we're still human. All right. So let's look at what we have coming next. Oh, 3 stars. Let's see what that one says. Or maybe we'll talk through these and man, can I solve that? Let's see. Write a procedure path that takes an integer n and a binary search tree. So from page 10, a BST that contains the integer n and return. We're writing a procedure called path that takes a number and a binary search tree that contains that number somewhere in there and returns a list of the lefts and rights showing how to find the node containing n. If n is found in the root, it returns the empty list. Okay. So this guy is taking in a binary tree, and we'll go and look at the definition of a binary search tree first, as well as a value to look for in that binary search tree. And then it wants you to give effectively GPS directions. It wants you to traverse that tree, giving left and right directions for where you need to go, where you need to turn in order to get to that value, and return that as a list. Does that make sense? Now, how can we decide whether to turn left or right in a binary search tree? Remind me, what are binary search trees?
A root number, the number's bigger than that, on the right side, less than that,
Okay, and somewhere in there, there's the equal sign. It's either left side is less than or equal to, and the right side's greater than, or the left side's less than, and the right side's greater than or equal to. So let's look at page 10 and see which definition they've used here. Usually less than or equal to on the left is the kind of the go-to definition. Let's see, do they call it BST? So can I? 93. I know, but no. Binary dash search. Ha! Nailed it. See, I didn't need any of your help. The funny thing is that I can solve the problems, but I can't use the book. It's like I've always been that way. Like the hard things I can do like not without too much trouble. It's like the easy, trivial things. It's like a monkey doing a math problem. It's pretty bad. All right, so a binary search tree can be the empty list. Nothing to search for, right? Or it can be an integer, followed by a binary search tree, followed by another binary search tree. And okay, well, so that definition does not tell us. Okay. Does it tell us whether it's less than or equal to on one side? Binary search tree. All the keys in the left subtree are less than or equal to. So what's what I said. So the left-hand side, everything is less than or equal to. Right-hand side is greater than. Make sense? So that's going to be our binary search tree for that one. What was that? 1.3 point whatever. This guy right here. All right, so if we're looking for the path to 17 in this binary search tree, we're going to check the top level. Not there. Is a 17 to the left or to the right of that? 17 is greater than 14, not less than or equal to, so it's going to be to the right. That's where we get our first part of our output, right. Okay, so now this was the left subtree, right? Let me copy this in here. It'd be easier to match parentheses inside of a scheme. Okay. All right, so this is the value at that node. That ends that. That ends. Where does this tree end? Oh, there it is. So this is the left subtree right here. So since we decided that a 17 over here, the value we're searching for, is greater than 14, it would be in the right subtree if it exists at all, correct? So we'll go ahead and record. I'll just start making our answer here. All right. And then we will go and look at that right subtree. That's the tree we're looking at. Make sense? Is a 26 equal to 17? It's not. Should a 17 come before or come after a 26? Should come before. So it's going to be less than or equal to. So we're going to record our next direction will be a left. And that's our left subtree. Is a 20 equal to a 17? It's not. Is 17 less than or equal to 20, or is it greater than 20? Less than or equal to? So we'll record our left. There's the left subtree. Is a 17 equal to a 17? It is. We're done. There's our answer. Right, left, left. That's how to traverse that tree. That make sense? Not too bad? All right, that's 3 stars. That should be, so we definitely need a second question then. All right, so write a procedure number leaves that takes a binary tree and produces a binary tree like the original, except the contents of the leaves are numbered starting from 0. For example, if we have an interior node foo, this is leaf 0, this is leaf 1, in terms of leaves we run into. That's the 0, the 1. This is leaf 2, that's this guy right here. This is leaf 3, this is leaf 4, here and here. That's going to be a very, very similar problem to the count reds type question. Make sense? So does everybody understand what's being asked there in 135? Now what's interesting here is, do either of those sound absolutely horrific relative to some of the other stuff we've done? Are they in the same ballpark? These are 3-star ones. These are way harder. What does that mean? We're getting better. But I don't want to let you go to your head. That's why I'm asking harder questions still. All right, so for let's see, we have so for Wednesday, we're going to do 135 and 134. 134, 135. And if you are going to the hackathon, which is it's closed now, we have everybody who signed up. I sent an email out to you asking you to sign up for the register for the thing and everything. I think both of you already did, right? So I think you guys are good. But if you talk to some of the other people on that list, make sure that they get signed up as well. I will see everybody on Wednesday.